AC.
Electricity.
DC.
Today we're demonstrating a new design tool, a web app that allows you to calculate the magnetic field from a circuit board trace and the output from a magnetic sensor. Here's the diagram. The app lets you define the PC board thickness, the copper thickness, the trace width, the current through the trace, the type of sensor, and the sensor supply voltage. We can also select zero board thickness for the trace on the top side of the board. We'll select a 0.09 inch 2.3 millimeter trace and 1 ounce copper. We'll enter 10 amps. There's a warning that the current exceeds the trace guideline for a 30-degree temperature rise, so we'll change to 2 ounce copper. Let's choose an AA003-02 sensor, which is popular for current sensing, and a 9-volt supply. The predicted output is 392 millivolts. Let's see how that corresponds to an actual measurement. We cut off sensor pins 2, 3, 6, and 7 to allow for room for the trace on the top side of the board. The sensor is powered by a 9-volt battery and connected to an oscilloscope. The yellow scope trace is the signal generator. Cyan is the sensor output. We ramp plus minus 10 amps through the trace. The output is 440 millivolts, which agrees with the model to within the sensor's sensitivity specification range. Here's how the app works. For narrow traces, the field can be approximated by Ampere's law, but the approximation breaks down for wider traces, which are needed for higher current. So the app does finite element analysis, breaking the trace into an array of thin traces. So to sum up, this app makes it easy to design non-contact current sensing. The advantages of this type of sensing are a wide current range, negligible insertion resistance, measurement down to DC, and inherent electrical isolation. Here's the URL. Click, email, or call us for more information or to order parts or evaluation kits.